We're going to continue talking around perturbation theory and stability of dynamics. In particular, we're going to move and shift our attention to talk about what's called Floquet theory. Floquet theory is really concerned with thinking about the stability of periodic solutions. So this arises in many situations where you have some kind of time-dependent system, where you have periodic solutions that are important to study, and you'd like to understand the stability of these periodic solutions. So Floquet theory gives us a way, which is a generalization of linear stability analysis, right, which is perturbing around solutions that are, let's say, some time-independent solutions, and then looking to see if those solutions grow or decay. Here we're looking at solutions that fundamentally have some kind of periodic behavior, but we'd still like to know, do those solutions grow or decay under perturbation? Are they stable or unstable? And these arise in lots of different physical systems. And so Floquet theory is really important and often not covered in many courses, yet it's somehow very fundamental to understanding a lot of physical processes. So the way to start with this is to start thinking about what's called a Poincare map. So although we are interested, of course, in the entire dynamical trajectory of the system, what we're going to look at is, in some sense, a map from one period to the next. And the way we're going to construct this is to start thinking about it from the point of view of a flow map, which is to think about the state of the system at P of n mapping to P of n plus 1, where this flow map phi here is taking you over some period t to the next mapping point. Oftentimes what's done in these dynamical systems is we define what's called a Poincare cut or Poincare section. And what you do is you look at the dynamics, and every time it hits this Poincare section, you mark it. And that is, in fact, one of these P of n's. So I don't look at the entire trajectory. I just look at the trajectory going through some section that I've defined for my dynamics, and then look to see what are the dynamics on that section. I'm going to give an illustration of this in a moment in pictures. And so this is one way to start thinking about how to quantify these periodic solutions, which is I want to look at where is this solution after every period, right? And so stability really comes down to this idea here that when I look at these Poincare maps, P of n plus 1 mapped through this flow map with P of n, that in fact stability is really giving you this idea that as I go through this flow map, P of n plus 1 equals P of n. In other words, I converge so that I'm on some kind of periodic orbit. That's actually what this implies here, right, is that if I define some section in some parameter space and I look at the trajectories always coming back to some cut in the space, if it keeps hitting the same point, that means this thing has achieved some kind of stable periodic solution. An unstable periodic is one that wanders away from that. So then when we look at this flow map, then P of n plus 1 does not equal to P of n. And in fact, every time I come through here, I start to get further and further away from the point I was originally. And that's what this inequality means here, is that P of n minus P of n minus plus 1 is greater than P of n minus 1 minus P of n. In other words, I diverge from some kind of periodic orbit. So these are very natural ways to think about stability. They generalize the concept of linear stability that we've been talking about previously, right? Which is when you perturb a system, you ask the question, does the perturbation grow or does it remain small or go to 0? In this first one, the perturbation remains small and goes to 0. In other words, you fall into a periodic orbit. Here, this one here tells you that you wander away from that periodic orbit. And you're doing this all now in the context of a flow map, which maps you over some time. So let me just show you what this looks like. This is some kind of cartoon of what this looks like. My dynamics is happening in, let's say, some three-dimensional space. And I define a two-dimensional Poincare section, which is this plane right here. So every time the dynamics goes through this plane, I mark it. So those are the blue points. So I start here with my initial condition. It starts to evolve, goes through the plane. I mark that point. Now it evolves. Hits this plane again, I mark that point, and you can see here P0, P1, P2. These are the markings of where the solution is hitting this Poincare section, and this defines the Poincare map. So the Poincare map tells you how P0 goes to P1, P1 goes to P2, and so forth. So this is the idea. So normally what you say is if I'm working in some n-dimensional space, you define some n-1 dimensional Poincare section, and you look to see what happens along this section over time. And of course, if I had a periodic orbit that would just, if all these points started to cluster and fall onto a single point, that means in this higher dimensional space, I'm on some periodic trajectory, and that is stable. If I start to wander away like I'm doing here, then that means that periodic solution is, in fact, unstable. So this is one way to start thinking about the stability, or a way of characterizing periodic orbits. So Poincare maps are really important in these flow maps. And really just, again, looking at the behavior after every period. So how do we actually do this in a more mathematical way? So what we're going to start doing is working with what's called Floquet theory. So Floquet theory is all about thinking about these periodic solutions and starting to address, can I explicitly compute stability? And this is what Floquet theory is going to allow us to do. So I'm going to start off with a simple equation, which is what's called, is a second order linear differential equation with some coefficients P1 and P2, where the coefficients P1 and P2 are in fact periodic. So there's some period T, and where P1 is just shifted over by T, and P2 is shifted over by capital T as well. In other words, these functions are periodic with some period, underlying period capital T. And what I want to do is look at periodic solutions to this and address their stability. By the way, if P1 is 0, so in other words, if I drop this out, that's called the Hill's equation. And it's a pretty famous equation for looking at periodic solutions. So I want to do a full Floquet theory on this here to illustrate what you would have to do in practice to compute stability of periodic orbits. We can work this out completely from start to finish, and it gives you a recipe for being able to compute the stability of periodic orbits using this Floquet theory idea. So first, what do I want to do? Well, it's a second order differential equation, and let's assume that I can find two linearly independent solutions. Let's call these x1 and x2. Then I know I can represent the solution as just some linear combination, because this is a linear problem, as a linear combination of those two with some arbitrary constants C1 and C2, which I can determine from, let's say, the initial conditions, right? So I specify the initial position, the initial velocity, and I could get C1 and C2. So this is a generic solution to that problem. And so what I'm going to do is start to now, and so far this doesn't take into account anything around sort of the periodic structure that I'm going to start to now frame for this. So what I want to do is start looking at periodic solutions. And what does it mean to have a periodic solution? Well, if I have a periodic solution, then I should be able to take x of t plus t. In other words, take my solution up here, shift it a capital T into the future. And by the way, all I did was I took my governing equation and I just shifted all the time by some capital T. So this is a generic transformation, right? I just shift the origin of time over to capital T. And notice P of 1 t plus capital T is equal to P1 of t. P of 2 capital T is equal to P of t, P2 of t. So if you look here, what it's telling you is if I have a solution x of t, then x of t plus capital T is also a solution. That's what this is telling you here. So this is a very simple calculation, right? You're just saying I can find a solution, and the solution shifted over by capital T is also a solution. And I just showed that right there. So that's important. And it's going to allow us to now frame stability criteria for these periodic solutions. In particular, what I'm going to do is I'm going to develop this theory around generating two new linearly independent solutions. So remember, I started off with two linear independent solutions, x1 and x2. And I'm going to define two new linearly independent solutions, x1 t plus capital T, x2 t plus capital T. And there's some linear transformation that takes me from my old linearly independent solutions to my new ones. So there's some, coefficients a11, a12, a21, a22. So there's some transformation that I can use. Remember, there's only two linearly independent solutions, but I can modify them in this way. So I want to represent my linearly independent solutions instead of by this x1, x2, instead by the solutions shifted over by capital T. This is generic. I've not done anything wrong. I'm just trading out my linearly independent solutions for two new ones that are linearly independent. But this has great implications for us, because I know those solutions that are shifted by capital T are solutions to that differential equation. And so I have this mapping then in matrix form that looks like this. X of t plus capital T is some matrix A times x of t. Okay? So this is the transformation for my solutions shifted over some period capital T. Now what I'm going to do with that matrix A is I'm actually going to do an eigenvalue decomposition of that matrix. So what I'm going to do is say, well, go look for the eigenvalues and eigenvectors of the matrix A. And what I know about eigenvalues and eigenvectors of a matrix is it often allows me to come back to linear problems and diagonalize them. In other words, write them in a new coordinate system where now I have diagonalized dynamics, so all the components essentially evolve independently of all the other components. This is one of the great powers of an eigenvector decomposition, is it allows you this way to represent things in this diagonalized coordinate system. And by the way, we did this quite a bit in the early parts of this course when we were talking about eigendecompositions. That was the power of the eigendecomposition, is this representation of the system in a diagonalized coordinate system, allowing us a great flexibility in terms of finding solutions and representing solutions of different boundary value problems. So this is my transformation to an eigenvector coordinate system. And so what I'm going to do is say I'm going to define x and make a variable, another variable transformation. X is going to be equal to v times little v. In other words, I'm going to take this into my eigenvector coordinate system. So there it is there. And so what this is going to allow me to do when I put this in and I put it into the governing equations, here's what you get. It's in diagonalized form. In other words, this little vector v, which is my new coordinate system, is v of t plus t is equal to this diagonal matrix times v. I've just diagonalized this coordinate system. And what it's telling you is that each one of the components is independent of the other components in this frame. So one way to look at that is then now is component by component. So now that it's in diagonal form, I can say, well, the first component of the vector v, let's say v1, t plus t is equal to eigenvalue lambda 1 v of 1 t. In fact, you could do this for each different component, and you can see that the eigenvalue just shows up right here. So that matrix A, its eigenvalues are showing up right there, lambda as the lambda j. And in fact, this is one period in time. What if I wanted to go n periods of time into the future? In other words, n periods ahead in the future, this is v of j of t plus n of t. So this is how many periods I'm going to go in the future. And all this is going to do by this formula is I keep repeating and applying it. It's going to give me this eigenvalue to the nth power v of j. Or if I take the norm of both sides of this equation here, I'm going to get the following relationship here. And here's the observation that we need to make. The solution in the future, n periods in the future, is going to be what it is now times this multiplicative factor. And what you really care about is what are the values of those eigenvalues. In particular, if here's the stability criteria, basically. If those lambda j's are less than 1, okay? So if the magnitude of the eigenvalue is less than 1, then this thing is going to go to 0, right? Because you're taking this thing to the nth power. However, if it's greater than 1, this thing will go to infinity. And it'll be unstable. So right away, I have my criteria for stability. All I have to do is find those eigenvalues, determine their absolute value is bigger or less than 1. If they're exactly 1, then I have exactly a periodic solution, right? If these things are 1 directly, then it just tells you this will be 1 here, and it just tells you my magnitude of the vector at the initial time is the same as it is way into the future n periods. So you can see we've reformulated this stability problem as sort of an iteration on this mapping. So this is kind of, in some sense, this is your flow map right here for this system is just all you have to do is multiply it by the eigenvalue lambda j. That is the flow map in this coordinate. So how do we compute these Floquet multipliers? In fact, we're going to look at these lambda values because they seem to be the key to understanding stability. And I'm going to come back to here and start understanding what happens to v of j times this exponent e to the minus gamma j t plus t. And, well, what I know from this here, this guy here, this is going to be equal to lambda n v of t times this exponent here, which now I can break it up into two components. One which is e to the negative gamma jt times v of jt times, here is the exponent over a period. And what I know is for periodic solutions here, I need this here to be 1. So for my periodic solution, that's 1 here. Then I have, this is my flow map right there. This is the flow map where the lambda j are what are called the Floquet multipliers. And this is the characteristic equation here with this term right here with this e to the minus gamma jt. So this defines then my flow map so that I get this return map, so this periodic solution. So this is one way to start thinking about Floquet theory. I've set this up in a coordinate system, which are the eigenvectors of this transformation of this matrix A, which takes you from the x of t fundamental solutions to the x of t plus capital T fundamental solutions. By just looking at that matrix and its eigenvectors, I have all the information I need to compute the stability. So how do we actually compute this in practice, though? That's what we want to do. Just recall that for periodic solutions, I have to have these conditions here. And what I want to do next is actually just walk through a very specific example of what we need to compute then from a system that has periodic coefficients, and what do we actually need to compute to get this. So what we're going to do in computing the Floquet multipliers is we have to compute this map from the solutions, fundamental solutions that are just given as functions of t, to the fundamental solutions that are given at t plus capital T. One way to do that is to start considering the following initial conditions. Let's say for one of the fundamental solutions, x1, that at time 0 its value is 1 and its derivative is 0. And for x2, which is linearly independent, by the way, its initial condition is 0 and its derivative is 1. So the nice thing about this solution is you have the Wronskian easily calculated from here, which is 1. Okay, and these are basically linear independent solutions, very nice initial conditions. And what I'm going to do with that now is ask the question, what does my mapping look like from time t to time capital T into the future? And I will start this at time 0. So put in time t equals 0. Remember that this thing here was, I'm going to map my fundamental solutions from one set to another set, which are advanced t plus capital T into the future. Take t equals 0, and what it tells you, x1 at capital T and x2 at capital T is equal to this matrix here, which is x1 at 0, x2 at 0, x1 at 0, x2 at 0. So this is going to allow me to construct that matrix A explicitly. Okay? So I'm mapping this using my initial data. This holds for any t, but it specifically holds for time t equals 0, where I have the initial conditions. So the matrix A then, when I go to compute this, I can actually compute what these matrix coefficients are when I put in these initial conditions here. And what I find is that the matrix A is given by the following set of values. It's x1 at t, x prime 1 at t, x2 at capital T, x2 prime at t. And so what I can do now is compute the eigenvalues. This is exactly what we did for the Floquet multipliers, which is I can just say, what are the eigenvalues of this matrix A? That's what we were looking for before. So here you go. Your characteristic equation that comes out is this. This is all equal to 0. I forgot, there's a bracket missing here, equal to 0. And so this is a quadratic equation, and you can solve for this. And you can solve to say, what are the values of this lambda, right? What we want to know is lambda inside or outside the unit circle? And if you do a little bit of work here, we define this quantity delta, which is right here, this is looking like the Wronskian at time 0, then this whole thing comes down to looking like this. Lambda squared minus 2 alpha lambda plus 1 is equal to 0. It's my characteristic equation. And those are the roots of this equation. Alpha plus or minus square root of alpha squared minus 1. So the value of this alpha very much matters, right? Whether it tells me a lot about what the eigenvalues are. Remember, what I'm looking for is to see, are these eigenvalues greater than 1 in absolute value or less than 1 in absolute value or equal to 1. If they're equal to 1, they're right on the unit circle, and I'll get periodic solutions. If they're less than 1, I'll have a stable orbit. Right? I have stability of the flow map, and if it's greater than 1, I have instability. So really, I want to make sure that this thing here, its eigenvalues are 1 or less than 1, and then I'm fine and have stability. And if anything's bigger than 1, everything's going to go to infinity. All right, you also have this constraint. It's not that hard to show that lambda plus times lambda minus is 1, so that's a nice constraint on this thing. And so one of the interesting things is oftentimes you'll get complex eigenvalues, and those are actually quite nice because they come in complex conjugate pairs, satisfy this, and oftentimes will be stable solutions. So let's actually in fact look at this. So the alpha that's sitting inside of this here, okay, there it is. There are some conditions where we can make some conclusions. If the absolute value of alpha is greater than 1, there's one bounded solution and one unbounded solution, and it's unstable. Basically, what you have is a saddle. Let's go back and see this. So if alpha here, check it out, if alpha is bigger than 1, right, then this thing here will just be the square root of some positive number. And so you'll have alpha plus that number, alpha minus that number. So you're going to have basically a positive root and a negative root. This is a saddle in that case. And what we know about saddles is that they're unstable. So there's a stable direction and an unstable direction. So if alpha is bigger than 1, you're guaranteed to have this saddle, and the periodic orbits are going to be unstable. Okay? However, if alpha is less than 1, right, then this thing here, right, is going to be take on an imaginary values. And if alpha is less than 1, the real part's also going to be less than 1. So if I look at its absolute value, I'm going to be in good shape in terms of stability. In fact, if alpha is less than 1, the eigenvalues are complex conjugate pairs that reside on the unit circle. So in fact, you can show that they're going to sit on the unit circle with that real imaginary parts, and you have stable solutions. So those are the two conditions you have available to you. And what we did is we got this simply by computing solutions, one solution with this initial condition, one solution with this initial condition, and once we have those, you can compute here the eigenvalues then of this matrix A. Remember, x1 satisfies the initial condition 1 is the initial condition and 0 for its derivative. x2 satisfies 0 as the initial condition, 1 is the initial derivative. Once I have those two solutions, all I got to do is compute the eigenvalues for that, and I have everything necessary to compute the stability. In fact, with this, we can do a little bit more manipulation in algebra to compute what's called the Floquet discriminant. And the Floquet discriminant is basically going to tell me, is alpha less than 1 or greater than 1? So the Floquet discriminant is really trying to measure this equation here, right here. Is alpha less than 1, absolute value less than 1? And the Floquet discriminant, gamma, absolute value, is given by the solution x1 at t plus the derivative x2 at t, and this thing here has to be less than 2. So you can work this out, and once you work this out, this comes right from that quadratic equation. That's the stability requirements. The Floquet discriminant being less than 2 guarantees you stability. So that's what you're going after in this Floquet theory. So for this simple problem, like the Hills type problem, this is the condition for stability. You can compute the Floquet discriminant, show it's less than 2, and then you're guaranteed to have stability. Now what's important about this is that, in fact, generically what you'd want to do is compute this Floquet discriminant. You can do this numerically as well. This is important because if you have a system where you can't just, here we can write down the solutions in a very nice closed form way, but generically the way you would solve this is you would actually do this computationally to solve for this Floquet discriminant, which is to run your solutions to the future and compute these terms here just from numerics and grab this and show that it's less than 2. In fact, we're going to do that in the next lecture. But the main thing I wanted to highlight here is what we've talked about is this idea of a formal construction for a stability analysis of periodic solutions. And it was all based on having a fundamental solutions, and that in fact you have a fundamental solution. You can also write the fundamental solutions in a coordinate system that's shifted by capital T into the future, and there's a map between the two. And that matrix mapping the two, you just look at its eigenvalues and eigenvectors, and from that we can work out and compute this Floquet discriminant, which tells us exactly when the periodic orbits are in fact stable or unstable. And of course, we're very interested in stable periodic orbits because those are things that would be manifest in the observations of a system. I will talk more about this in regard to the pendulum problem in the next lecture, but at least here you have the basic construction of stability analysis for periodic solutions.